Okay, so this is a second video on counting, and I'm further into the counting notebook. This is where we left off, and we have the question, Professor Daniels has 7 books to place on a single shelf. How many different arrangements are possible? And the answer is 7 factorial, which in R we can type in as factorial 7, and there are 5,040 different ways Professor Daniel has to place those 7 books on a single shelf. We don't know exactly how many seats were at the round table, as traditions differ, and it's not historical, although there may be some historical basis for King Arthur. I'm not sure there's any historical basis for the round table. Um, but, um, and supposing there were 24 seats at the round table and that King Arthur always sat on a special seat, in how many ways can 23 knights of the round table be arranged? Well, this is weird because this takes it from a line into just, I mean, from permutations on a circle to permutations on a line. Why? Because King Arthur's seat is fixed. Okay. So there's just the 23 factorial ways, right, for them to be seated in a line, except um, the line has ends on King Arthur's right side and ends on King Arthur's left side. So there's actually 2 of them. So the answer here is 2 factorial 23. So that's a little odd one. If we're just counting, if King Arthur isn't special, then it is 23 factorial, right? So there you go. The key is that King Arthur has this special seat, and it takes some thinking to figure out how that changes it. It changes it into a line that has a different seat at the beginning and at the end because one is on King Arthur's left and one is on King Arthur's right. And here we have a poker pro who doesn't want to have a troublesome player seated to their left. Okay? And so there are 9 players. And again, we're interested in the seat on his left, so there are 8 factorial total ways for the players to be seated. Okay. But if we seat Daniel Ingranu and this Betty person on his left, right? And then we just choose any of the 7 factorial orderings, right? Then we get the number of ways that that can happen, right? So this is again factorial 7. And what is the probability that one of the amateurs is seated to Ngannou's left? Well, the same as for Betty, but times 2, right? So because there are 2 of the amateurs and they can't both sit on Ngannou's left at the same time. Okay. So given that Georgia license plates are 3 letters followed by 4 numbers, how many distinct ones are possible? Okay, so the answer we have is 26 raised to the third, right? There are 3 letters. And these letters can repeat. Um, and we just know that in license plates. It's not given to us, but that's how license plates work. And again, all 10 digits can repeat, so we have 10 to the fourth. And that's exactly how we type it, right, into R. And there you go. So that is a lot. 175,760,000 Georgia license plates, which is enough to cover every, license plate east of the Mississippi, right? So there's plenty of options there. Now we know that not all 3-letter sequences are allowed. Um, they do get rid of cuss words and things like that. They also sometimes rule out things like God, words that are going to maybe carry a meaning. And And the license plate bureau doesn't want to deal with that. So not all of these license plates may get used. Okay. For a new lottery, the players pick three numbers between 11 and 55 and three numbers between 55 and 99. If no number can repeat, how many different picks are possible? And it's important to notice that I don't calculate 55 minus 11. Why? Because that would assume that 11 couldn't be chosen, right? If 11 can be chosen, I have to do 55 minus 10 because I'm only getting rid of the 10, 9, 8, 7, right? I'm not getting rid of the 11. So I have 45 numbers for the first one, okay? And then from 99, I'm subtracting not 55, but 54, right? Oh, now this is interesting. So I have 45 and 45, which makes sense because between 11 and 99, there should be 90 numbers. That does make sense if you think about it, right? So I have 90, choose, but I can't do it that way, right? I've got to do 45, choose 3, right? Times 45, choose 3. All right, and let me make this all caps, right, so that we can kind of see that formula there. Okay, so I can do combin, oops, get rid of my all caps, combin 45 comma 3. I'm just going to square that. I can multiply it, right? I can do the times, or I can just square it because it is the same value. Okay. And there we go. That looks like 201,356,100 different numbers in this lottery. Okay, so among the 7 nominees for 2 vacancies on city council are 3 men and 4 women. With any 2 of the nominees, okay, well that one's easy, right? Any 2 is just 7 choose 2. Okay. And then any 2 women should be easy, right? We just take, there are 4 women, so sorry, combine 4 choose 2. Okay. And there's 6 ways to choose a committee with just 2 women, and then with 1 man and 1 woman. Okay, so let's call that one of each. So what's that? That's combin, right? 3 choose 1 times combin 4 choose 1, right? So there are 3 men, we're choosing one of the men. And then we're multiplying that by 4 choose 1. There's 4 women and we're choosing one of the women. Okay, so there are the 3 answers, 21, 6, and 12 for the 3 questions there. Okay, Mr. Jones owns 4 pairs of pants, 7 shirts, and 3 sweaters. And he has to choose 2 of the pairs of pants, 3 of the shirts, and 1 of the sweaters to pick for a trip. Okay, these are permutations. No, it doesn't order them. It doesn't matter the order in which they're chosen. Right, so it's combinations, right? And of the 4 pants, he's choosing 2. And then he's got 7 shirts, and from those 7 shirts, he's choosing 3. And then from the 3 sweaters, he's choosing 1. All right, so 4 pants choose 2, 7 shirts choose 3, 3 sweaters choose 1. So he has 630 different outfits he could choose from once he packs these and goes on the trip. He'll have 630 different ways to choose that. Suppose a true false has 20 questions. In how many ways may a student mark the test? Well, This again is base 2. You mark either true or false. So you've got T or you've got F. So you've got two choices. And there are 20 questions. So you have, what is that? 1,048,566 ways. Remember the little plus sign here opens up another cell right below the one the cursor is on. Okay, in how many ways may the same student mark the test if 10 questions are marked correctly and 10 are marked incorrectly? Okay, so if we say right and then wrong, right? What do we have? We have 10 rights and 10 wrongs, but they didn't say what order. So it basically we're asking, right? How many distinct orderings of the word, I'm going to put that in parentheses, are possible. Okay. And how many is it? Well, we have 20 factorial orderings, but we have to divide by 10 factorial times 10 factorial. Again, once we've made an arrangement, we can't tell the difference between any of the 10 R's and where they go. So there are 10 factorial permutations of the R's. And same with the W's. Okay. So let me hashtag that. Why? Well, because the answer to this is going to be factorial 20 divided by factorial 10. And honestly, I'm doing squared, so I don't need these parentheses. And even though there's a million ways to answer the test, right, there's only 184,756 ways to answer it if 10 are right and 10 are wrong. In how many ways can 5 persons line up to get on a bus? Well, that's easy. That's 5 permute 5, which is 5 factorial. Also, you'll notice that our permutation formula of 5 permute 5 works in exactly the same way. So it's 120 either way. And for number 10, in how many ways may these same five people line up if two people refuse to stand next to each other? Okay. Um, so those are the 5 people and the 5 slots, right? And let's just say that 1 and 2 don't want to stand next to each other. So what are the options? Well, the only ways that 1 and 2 could be stood next to each other is if they're together first or second or third or fourth. There's 4 of them. But instead of having 1, 2, I could have 2, 1. So there's 2 factorial times 4 ways that they would be stood next to each other, right? So the answer, the solution here, um, is to do what? We're going to do the 5 permute 5, but we're going to subtract out the 8 ways where they're standing next to each other, right? And so there are 112 ways for them to line up if 2 people refuse to stand next to each other. In how many ways can 8 people form a circle for a line dance? That's n minus 1 factorial here, so 5040 for 7 factorial. How many unique arrangements are there of the letters? Great, well, there's 5 letters, so that's 5 factorial. How many unique arrangements are there of the letters in greet? Okay, well, it's the same idea. There are 5 factorial ways to permute these 5 letters, 5 permute 5. But the two factorial ways that the e's can be permuted amongst each other can't be determined. You can't determine which e has come first, right? So the way to do this is we divide out by the 2 factorial for the two e's. So 120 for the first, for question 12, the solution for question 13 is 60. How many unique arrangements are there of the three letters? Okay, so first of all, I've got to count these letters, and let's see. And that's 4, 6, wait, there's 4 and 6 more. Yeah, 4 and 3, so there's 10 letters. All right, so let's get it. If we have 10 objects, right, there are 10 factorial ways to permute them. All right. The problem is they're asking about unique arrangements, and we have a lot of repeated letters, right? So we have the S's, we have 3 S's. So we have to divide out by 3 S's. Oh, but we have 3 T's. Okay, so we have to also divide out by the 3 T's. So let me put some parentheses here and we can keep track. Sorry, that was supposed to be times. So 3 factorial times 3 factorial for the S's and the T's. The I's repeat twice, not 3 times. The C is solo, the A is solo. 3 S's, 3 T's, 3 I's. That looks like we have them all. So we have all of the repeated letter the number of them factorial, um, dividing out. So we're dividing out by those repeated letters. So instead of 10 factorial, which is what, 3.6 million, we have about 50,400. How many unique arrangements of the letter statistics begin and end with the letter S? Okay, so in some ways this is counting, right? The 8 letters in the middle. Okay, so we're going to do factorial 8, but now there aren't the same number of repeated letters to divide by, right? I still have the 3 T's, so I can do factorial 3, and I still have the 2 I's, so I can do factorial 2. And is this correct? Well, not really. Why? Because we don't know which S was first, which S was last, and which S was included in the middle. So this is correct, except I have to multiply this whole thing times 3 factorial. Right? And that allows the S's to permute. And there are about 20,160 ways, therefore, for unique arrangements given these constraints. In a primary election, there are 4 candidates for mayor, 5 candidates for city treasurer, and 2 candidates. If you choose in every one, so you're doing from the 4 mayoral candidates, we're choosing 1 times the 5 candidates for city treasurer, we're choosing 1. And for the 2 candidates for county attorney, we're choosing 1. That's the answer. There's 40 different ways to fill out the ballot if they vote in all 3 races. If they exercise their right to vote or not to vote in any or all of the 3 races, we have 40 plus we have, right? What if they just voted in the first 2? Okay, or we have to add in what if they voted in the second 2? Um, right? And what if they voted in the first and third, right? That's 4 choose 1. times 2 choose 1. Okay, so that's 38 more elections if they vote in only 2, but what if they vote in only 1? If they vote in only 1, I have all 3 of the elections, but I have to add these. And that's if they vote in just 1 election. And so you're going to believe then that if I add all these up, if I vote in all 3 elections, if I vote in some combination of 2 elections, if I vote in just one of the elections, right, then I have 40 plus 38 plus 11 plus 1. Why plus 1? Because what if I vote in none of the races? There's exactly one way to vote in none of the races. So there are 90 ways to do so. Multiple choice question with 5 alternatives for each question, 15 questions. So this is just 5 raised to the 15th power, right? We have a 5-letter alphabet, and we're making a word that's 15 letters long, essentially. And again, R will actually evaluate that. A team of field hockey players needs to choose a captain and co-captain. Again, if the 2 captains have equal authority, I mean, I don't know. I don't know if the co-captain has the same amount of authority as the captain, or if they're just a backup in case the captain can't play that day. But if the 2 captains have equal authority, that's just 13 choose 2, right? However, right, if the 2 captains have differential authority, I mean, let's say that they're going to choose a senior to be one of the captains, and maybe the other captain is going to be a junior, and the senior is the one that's going to kind of be in charge, but the co-captain's there just in case, right? Then that's permutations, right? 13 permute 2. Um, so if we're just choosing 2 captains and they're the same office, it's 13 choose 2, and there's only 78 of them. But if we're choosing 2 captains and they have, differential authority, and there's 156. You're setting the combination on a 5-digit lock. You want to use the numbers 38175, but don't care what order they in. How many unique combinations are possible? This is just 5 permute 5, which is 5 factorial, which is 120. Right? You have the numbers, you know what they are, and there's just 5 factorial ways to permute them. Okay, student body of 50 students wants to elect 4 representatives. So that's just 50 choose 4. The representatives are the same office. It doesn't matter what order they're choosing in. Notice that R has a little bit of a rounding error issue. That appears to be 230,300. Because clearly we can't have a fractional person. A group of 17 horses start the race. How many unique finishing orders? And if you've been to the track, you know win, place, or show is a bet that you can put on. And win is first place, place is second, show is third. Okay. So there are 17 permute 3 ways to have those top 3 finishing orders. So there's 4,080 ways to choose them. 23 athletes at a meeting shake hands with everyone else. Again, we can do sum with the colon. We're summing up all the numbers between 1 and 22. Why? Well, the first athlete shakes hands with 22 other people. So the biggest number is 22, and then the next person shakes hands with 21, and then the next person shakes hands with 20 because the first 2 have already been counted when they shook hands. So there's 250 handshakes between these 23 people at this meeting. Euchre, We use 24 cards from the standard deck. How many 5-card euchre hands are possible? Well, this is 24 choose 5, right? Just to remind you, the total number of poker hands, since order does not matter, in the standard 52 deck of 52 cards, 52 choose 5, there are about 2.6 million different 5-card poker hands, okay? And then from a segment on a radio show, a disc jockey can play 4 songs if there are 8 to select from. In how many ways can this segment be arranged? And arranged, I'll say that's a permutation. I can see an argument for somebody wanting to do this as a combination, choose 4 songs, but it does matter what order you play them in. Closing time has to go last, for example, if you choose that as one of your 4 songs. Um, so if the order matters, then 8 choose 4 is the total number of ways, and Dr. Jams has 1,680 choices. So hopefully this has been helpful and an additional follow-on to the previous video. And hopefully we've gone over lots of the different ways of counting, but there's a few special ones that reappear over and over and over, and we've focused on those. Thank you very much. Have a great day.